Right, so the most quintessential form of induction is the application of changing a magnetic field through a coil of wire. So, say for example, we've got a coil of wire like so, and I introduce a magnet to this coil of wire. And I've got an ammeter hooked up to this as well. And it's going to indicate the direction of the current. Now, obviously around a magnet, we can imagine that we've got lots of lines of flux coming out like this. Now, notice what's going to happen. As I introduce this magnet here, what's going to happen? I'm going to draw this again when the magnet's closer. We're going to what we call link the flux through this ring. Now, what I mean by link the flux is you'll notice these are technically a hoop or a ring. Okay, so this is a ring here, and this is a ring here. So we've got a ring here and a ring here. And by linking that flux, what we're doing is we're creating this situation. Okay, we want to create a situation where this is the ring of wire, and this is the ring of the magnetic field, and these are going to be linked like that. And we call this flux linkage. So what I mean by that, and I'll draw that here. So here's the magnet again. So we've got a magnetic field line that goes into the ring and then comes out of the ring and comes back round. Goes into the ring, through the center of the ring, comes back round. And you're also going to have flux lines that don't go into the ring and come back round. But every line of flux that comes out of the magnet that gets linked is, when we're moving it in, is contributing towards a change in flux linkage. So we're changing the flux that's linked through this coil. So we're changing the amount of rings of flux that are linked through. As we move it closer, we'll get more of them that are linked through. So we've introduced, and we talked about this term flux linkage, and flux linkage is given the term that's flux linkage. And flux linkage is obviously flux that's linked through that number of coils. So when we have, in this case, we could almost say we've got two pieces of flux linked through one coil. So we could say, in a very simplistic way, that we had two flux linkage, because we've got two lines of flux and one coil of wire. So we'd have two flux linkage. So that's the idea there. But what's important in induction, and you'll see this practically in your classes that you'll take with me, is that actually it's not the flux linkage that it has, it's the change in flux linkage that's going to be most important in producing an EMF in this wire. So when we get a change in flux linkage, that's what's causing an EMF. So what we'll notice is when we introduce this magnet into this field, so we move the magnet from here to there, we get a change in flux linkage. And that causes this to flick to the side. Now, interestingly enough, when you move it is when it flicks. If you were to stop moving it, it would go back to its original position. Well, that's because when it's in the coil, so if you just put the magnet in there and left it there, you wouldn't see anything happening on this dial, because there has to be a change in flux linkage in order to get an EMF. Well, what's interesting about this as well is when you try this out in the lab, you'll naturally go, oh, what happens if I move it faster? So you actually move it faster in there. Well, we're getting the same amount of change in flux linkage, but instead we're getting it in a faster time. So the shorter the time it takes for that flux linkage to change gives us a greater EMF. So this time when I flick it, it puts it into that field, we get a greater flick to the right-hand side on the ammeter because the current has been induced in this coil of wire. So now we can introduce another term here. And this other term is time. Time affects the EMF. So a very low time, i.e. it moves very fast, means you're going to have a high EMF. Retrospectively, a long time means you'll get a very low EMF. So example, if I moved this magnet in very slowly, the change of flux linkage is the same, but we are going to take a long time over it, and so as a result, this doesn't flick quite as much. We might get something like that instead. And so we can actually put all this together in one big equation now. And that equation is known as Faraday's law of electromagnetic induction, where the EMF is equal to the change in flux linkage over the time. But there's actually, you may notice I have an equation sheet, and you may notice there's actually a negative sign in here. And there's a reason for that. And actually, poor old Lenz, this is Lenz's law. And Lenz's law is what indicates that this negative sign is there. Because, and I'll explain it in words first of all, and then I'll show you in terms of diagrams. Lenz's law states that the induced EMF acts to oppose this change in flux. So I'll write that down. So the induced EMF acts to oppose the change in flux linkage. Okay? And I'll show you diagrammatically what I mean on the next sheet of paper. So, as we said in the previous picture, we had a coil of wire. And I'm actually going to draw this from a different orientation here. Now, you'll notice that I said that the dial on the ammeter flicks to the right. That means that the current in this wire, when I introduced that, was flowing in that direction through the coil of wire. So there's the coil of wire, and that means the current is moving in that direction. Notice that I introduced a flux in that direction. So I acted to introduce a flux in that direction there. And you could almost represent these flux lines coming in as crosses, because as that convention is pretty standard. So we've got, this is the flux that I'm introducing from the magnet. Well, Fleming's right-hand rule actually comes back in here because this helps you decide which direction the current is actually flowing. Well, as I said, we notice the current flows in that direction. So I'm going to add a few more arrows just to show that direction of current here. So using Fleming's left-hand rule, we can actually show the direction of the magnetic field around this wire. So notice that my thumb points in the direction of the current, so the direction of the magnetic field as it goes around there is in this circle here. So if you look, my fingers are then pointing upwards, back up towards you right now as a result of the current flowing in this wire, which means there's a magnetic field around that wire which is opposing this change in flux from the magnet that's coming here. So go back to the idea of Fleming's right-hand rule, so or just the right-hand rule even. So if we have a wire that's got a current flowing through it, it will be in that direction, so the magnetic field goes in that direction. Other way around, if the current is coming out, right-hand rule, that means the magnetic field is going around the other direction. So we're using this idea to show what's going on here. Now, it's an observable fact that when you change the magnetic flux linked, i.e. the red in this instance here, I've lost my red pen, actually, I think it might be orange. So when you change the flux linkage, so this is the change in flux linkage that I'm introducing here, I'm introducing it in that direction, then we are getting a current which acts to oppose, or an EMF, apologies, an EMF which obviously leads to a current, which acts to oppose the magnetic field that's right here. So what we would observe as a result of the wire at this point, it would have a magnetic field that's like that. And that makes sense because if you think about it, if I was to turn this on its side, and you look at this, it goes around the wire. So this is going around the wire. So it's going out on that side and then coming back in on this side, which is why I'm using a spot to represent the magnetic field inside as a result of this coil of wire right here. So let me just write that down in a few clear points. The induced EMF leads to a current. And that current, as opposed to these rules, leads to a magnetic field. That magnetic field acts to oppose the change in flux linkage. Okay? It acts to oppose it. So we've got the induced, the change in flux linkage, the red crosses, that's what I'm introducing. The wire creates a current to oppose that change in flux. It says, hey, stop introducing that flux and I'm going to try and oppose it. And as a result, we get a current produced in this situation. So you might ask yourself, what happens if I take away flux? So say, for example, I remove flux from this situation. So as I remove the flux, then we can consider the opposite effect to occur. So let's go back to the wire with the ammeter at the bottom here. Now, if we change it so that the flux that I'm changing is a negative change in flux, so if I get a negative change in flux, what happens is I can draw the spots that represent that flux going in this direction. This also could mean that a flux was being introduced from the other direction as well, by the way. And as you can well think, the current is going to be the other way round this time. So the current is going to be the other way round. It's going to go this way. And as you'd imagine, this ammeter will flick to the other direction. Well, why? So based on what we can see here, if we use the right-hand rule, what's happening is if I put my hand down, my fingers go into the center. My fingers, I've got to get my hand the right way around here. My fingers go into the center and out the outside of it. So the magnetic field as a result of this looks like this. And so the idea of that, again, is the induced EMF creates a current. So now we've got a current. This leads to a magnetic field. This magnetic field acts to oppose the change in flux linkage. And so as a result, we get the opposite current observed in this situation. Whether you're introducing or taking away, or you're introducing a south pole as opposed to a north pole, you're going to observe these differences because you're introducing a negative flux when you introduce a north pole. So it's like introducing a magnetic field that's going this way. So if I was to put the south pole of a magnet coming in, it would be like introducing this, which would be dots. And so on and so forth. So you've got to get your head around all the different kind of situations that can occur. And as long as you have an awareness of these kind of concepts here, you can get your head around it. You can say, yes, I have an induced EMF which creates a current in the wire. This leads to a magnetic field around the wire, and that magnetic field acts to oppose the change in flux linkage. And it's all down to your understanding of the right-hand rule in this case to show that the opposing thing occurs. And hence, this all leads us to the fact that we have a negative sign in the flux in the induction equation, which is change in flux linkage over the time. And so you can see here that the negative means that if I get a positive change in flux linkage, then I'm going to get a negative EMF. If I get a negative change in flux linkage, I'm going to get a positive EMF because I'm going to have negative negative. So we're going to get both observed there. So just bear that in mind. I'll write that down. A positive change leads to a negative EMF, whereas a negative change leads to a positive EMF, because they're always in opposition in that case.